Thanks to the organizers for having me here. This topic will be a little bit different from the general flow of things. I'll not talk about EIC as such. I'll talk more about RIC and LSC physics, but there is some overlap between these discussions. So maybe you'll find it interesting. This is work done with two postdocs, Ankita and Balbir, last year. And what we analyzed was looking at substructures in heavy ion collisions. And the EIC will provide a lot of new information about the structure of the nucleons, especially in the nuclear environment, especially the initial state. But another aspect that has been discussed in the morning also is collectivity. And this is one topic that has been explored extensively at RIC and LSC. So, and jets are useful hard proofs of these collectivities. So, and there is a lot of data on jets from LSC in particular, and also from STAR now. The data is on jet overall yields, jet substructures, which looks at the longitudinal distribution of particles in the jet, like the fragmentation functions, jet shapes, which look at the transverse structure of the jets. And there's more data on tag jets also. So it's interesting to look at and try to see if you can learn something about the QGP from this large set of data. So Angularities is one of the substructures that has been studied for a long time. Just to set the stage, we can look at think about angularities in this manner. So you define some observable tau, where you collect this particular quantity from all the participants in the jet. So the fractional longitudinal momentum of the particle and the angular radius to the power of to some power. So there are a few things to keep in mind. So you need a less than 2. And actually, for technical reasons, it's preferable to use this power to be such that A is actually less than 1. And the intuition is that if you have wider jets, then they'll have a larger value of the angularity, and narrower jets will have smaller, and you can change the distribution by changing this power. Okay, so in particular, one observable that has been studied a lot is called thrust. A equals to 0. So basically, it goes as angle to the power of 2. And so suppose you have a jet direction in particular, in some direction n, and we are looking at small deviations around this jet direction. And that means that delta R is small, so tau is much, much smaller than 1. And now the question is, how does this distribution look like? Of course, if Z is large, then that contributes significantly. So those collinear modes have this sort of scaling in momentum, which basically in light cone coordinates is going in a particular n direction. And this gives some contribution to this observable. In addition, ultra-soft partons also contribute to it. They have a smaller value of Z, but they have delta R, which is larger. So they also contribute equally to the observable. So these are the two modes that contribute to your angularity. And this is nicely summed up in this particular plot. So these are the soft modes, which are soft. Basically, they don't have, lambda is a quantity which is smaller than 1, related to tau, basically. And they are soft because they have small momentum components. But as we saw, they contribute with the same strength as the collinear modes. And then far apart from that is the hard process. Okay, so this, as I said, has been studied a lot, and the technique that helps you study it easily is soft collinear effective theory, where you focus on the soft and the collinear modes which contribute to the observable. And the hard modes, which are off, as we saw, these can be integrated out, so their effects just come simply in an overall factorization formula. Okay, so this is all very fine. So so then basically the idea becomes this, that you have a hard scattering process, and then what you would see is that, okay, after this hard scattering, you get modes which contribute to your observable, which are the soft and the collinear modes. These can be described in this EFT, and this just gives you, as I said, in the factorization formula, some hard matrix element. Okay, so this would be the basic picture to describe this process, and the thing is, this is an intrusive process. You don't care about what happens to the other particles. You just want to measure jets with a particular angularity, and that gives you this observable. Okay, so right. So this is the basic setup. There's a little bit of a complication because you don't measure just angularities of the observables. What you do is first measure jets with a particular R. So maybe before I go that, if this diagram that I've written down, just formalized in a expression, just gives you this. So you have initial parton densities. Then this is the hard process, H. And then the soft collinear modes give you the dynamics, which gives you the observable tau. Okay, so the slight extra step that you have to go through is because you don't actually directly measure the angularities. You first select on jets with a particular radius. So radii 0.2 to 0.5, this sort of a range, and then measure the angularities of these jets. And this formalism was developed by Ringer and his collaborators. So what you have to do is you break this part into two pieces, one which tells you that you have jets of a particular radius r, and then get a particular angularities out of it. Okay, so that this breakdown is just this extra piece. And now the things that you have to focus on, once again, are these collinear and the soft modes. So I've just separated them out because they happen to live at different scales. So these two contributions are the things that you have to take care of. Okay, so this is useful because now you can just focus on these effects, which are different in the PP and the heavy ion conditions. Okay, so so this separation just involves a couple of steps. So you separate the Lagrangian in terms of the soft and the collinear fields. And the collinear field Lagrangian has this form for the quark jet, similarly for the gluons, collinear gluons. And I guess these technicalities won't be so important. So the key piece that we need is that there is a decoupling between the soft and the collinear modes, which is actually what was used in writing this separation between the jet and the soft function. So the collinear dynamics completely happen here, and the soft dynamics happens here. And this turns out to be useful when we look at the lead problem, because the collinear fields are the ones which will interact with the medium and get modified, and that will help us. This sort of a rewriting helps us in pinning that part down. Okay, so similarly, you can write the parts which give you the soft dynamics, and these can be also taken into account. Okay, so maybe just to complete the story, you can just write operator definitions for the collinear and the soft functions. So the soft function involves the soft fields. These are the collinear fields. And now the only thing that you have to be careful about is that you have to calculate everything at the same scale. So for that, you just write down the renormalization equations for the collinear and the soft fields, and mash them, and then evaluate the cross section that we had written out. So this has been done before, and then there's data now. So for example, this is data from Alice for PP, and for a particular PT bin. And this sort of factorization works well. There is one thing that you need to take into account here. You need to take into, so the expression I wrote down was a proton level expression. And to match it to data, you have to do hadronization also. And there is, you can parameterize the hadronization by some sort of a convolution with some soft factors. And it turns out that you need one undetermined coefficient to fit to data. The nice thing is that that coefficient does not depend on, does not depend on A. So for different powers that you have for this angularity observable, you have the same, you have just one fitting function, one variable that you have to fit, and the data really doesn't look too bad. Though one thing to note is, so these are these light lines, which give an idea. So things below this are really not governed by highly non-perturbative physics, and things above it are perturbative. So that's something that you have to take care of, but otherwise, this looks quite reasonable as far as PP is concerned. Okay, so so that sort of forms the baseline, and now to see what goes on in heavy ion collisions, it turns out it's useful to rewrite this in a slightly different fashion. The collinear dynamics that we described here in terms of this operator definition, it's slightly difficult to see what happens in a medium to this sort of a function. But it's actually possible to rewrite this collinear function or the jet function in terms of parton evolution kind of a picture. where you have some sort of a observable that you're looking at, and you have a parton which is going through this, let's say for now, just in PP, which is going through and is splitting again and again. So this is the usual D-glab kind of a splitting kernel. And this, this sort of rewriting of the jet function also gives you exactly the same form of the jet function for the PP case. So there's nothing, there's no new thing that comes for PP when you do this. But for heavy ion collisions, this turns out to be a useful rewriting, because then we know how to include medium effects. The medium affects the splitting functions, the P of splittings, so modified from the general D-glab kind of an evaluation. And then you can capture the medium dynamics. So, so the actual jet function just becomes the vacuum function plus a medium modified function. And these medium modified functions have been studied in various formalisms and approximations. The physics is kind of simple. It's medium-induced Bremsstrahlung. And the particular formalism we use here is where these medium-induced processes come through Glauber gluons. So you're exchanging off-shell gluons from this background thermal medium. So there are these thermal medium fields, and this delta is the propagator, which is the gluonic propagator that's mediating interactions from the medium and the, between the medium and the collinear fields. Okay, so this tells you what the interaction is, and then you just use this interaction. This would be the gluon exchange, which happens between the collinear mode and the medium. And the main thing that you have to take care of, as people have shown, several people have shown before, is that you have to maintain coherence. And this is done either in an opacity expansion or using the BDMPS approach or some other approach, but you have to maintain the fact that there's an LPM effect that comes in at small frequencies. Okay, so so for example, if you look at the interactions in the small gluon energy limit, it has some form like this, and you can see clearly there are effects of coherence that you have to take into account. Okay, so so that basically sets up the basic formalism for medium-induced processes. You have a modified probability of emission or the splitting function, as you wish, and that gives you the correction to the collinear or the jet function. Okay, so that basically is, sets up the problem completely. So you need to model the medium. So in this approach, we were, this was the first thing that we were trying to do. So we use a simple model for the medium. And with that, you get some these kind of results. So so these are distributions for jets with R equals to 0.2, 0.4. The spread here is just shown for changing the scale, renormalization scale. Mu, we varied it from PT2 to PT. And okay, so you have to specify the PT range. So this is of interest to Alice. These are ranges which are kind of similar to what have been used in Alice. So in this particular plot, I've shown what happens for A equals to 0 and the most central collisions. Okay, and let's look at this right plot first. So here you can see basically the effects are small, but the tendency is that in heavy ion collisions, the angularity distribution is shifted towards the left, it becomes narrower. And the interpretation is that there is additional medium-induced emission at intermediately small angles. And also, one thing that you have to take care of is that a jet with particular PT that comes in the lead-lead collision comes from a higher energy and starts being narrower from the jet in PP. So that also shifts your distribution towards the left. Okay, so the second thing that you can look at is how different PT bins fare. So this is once again the same plot as before. So for the PT bin of 40 to 60, and you see that the effects are larger if PT is larger. Okay, and once again, this is for the same A equals to 0, which corresponds to the thrust. Okay, and now it looks like the distributions are kind of very, very similar for PP and lead-lead, but you can see the effects a little bit more clearly if you take the ratios. So once again, the error bars here only take into account the error bars associated with the scale variation, not for example, the medium properties, etc. But you get distributions of this kind. So you see that in lead-lead, you see a bit of an enhancement at small taus. And then you get the integrals are taken to be 1, so you get a corresponding suppression at larger taus. Okay, and so these are results for 0.4 and then 0.2. And one thing to note is that in the formalism we use, if tau becomes comparable to R, then you can get very large corrections, power corrections. So you can't really trust the formalism beyond tau equals to R. So, so this will be this is not under good quantitative control, but this looks in much better quantitative control. Okay, so yeah, so this is, here you can really see that there is some difference between the heavy ion and the PP jets, and really the difference does depend significantly on R as well as E. Okay, and one thing that was a little bit interesting that we found was that for centralities which are next to each other, the two most next to each other, closest to central collisions that we consider 0 to 10 and 10 to 30%, the distributions actually looked quite similar especially for A equals to 0. I mean, except for the smallest tau A bins, the differences were very, very small. And this part of this is due to the model that we consider for the background medium. But also at small PT, there are other observables which for these two centrality bins are not very, very different. So maybe there is some something to it. It would be interesting if Alice can observe data for these for the second bin that we have here. Okay, so actually there is data, but so the groomed observables we have not studied, but all the calculations I've shown here to you so far are for ungroomed observables. And the trend, okay, turns out to be just the same as we expect, but I didn't compare the data with our calculations because, especially for the r equals to 0.2, a lot of, qualitatively things look similar. With the large error bars, things are kind of similar, but with the r equals to 0.2, a lot of the dynamics that happens close to tau equals to 0, where we expect a lot of non-perturbative effects. And our modeling of the non-perturbative effects, especially in the heavy ion collisions, is very, very simplified. So, so this is one of the reasons we didn't come. Okay, so so that's basically the story that jet substructure could be an observable which can help us study some of the finer properties of jet dynamics in the medium. And using these medium modified splitting functions, you can calculate these observables semi-analytically, at least in a simple background setting. And you can get the qualitative features right. But to do the quantitative analysis is maybe is kind of challenging. Okay, so before I go, the same sort of observables definitely will be studied at the EIC also. But there, the collective dynamics in the final state are not expected to be present. However, it's a much cleaner environment compared to the heavy ion environment. And quantitative comparisons with data for perturbative calculations of observables would actually give additional constraints on the initial state, which should be additional to, for example, just looking at yields and distributions of single particles. So with that, I'll stop and wait for questions.
Thank you. Other questions? Yeah, go ahead.
Will change? Yeah. So something like, no, where there was r equal to 0.2 and 0.4 plot, right?
Yes.
So if I look in this, the amount of uncertainty from 0.2 to 0.4, the relative uncertainty between PP and lead is quite drastic, right? With the radii, it's changing. So is there an intuitive way to understand the change in uncertainty ratios? Like for 0.2, the uncertainties are similar, the thickness of the bands.
Right.
And for 0.4, they're quite different along the angularities.
Yes.
Yeah, so is there an intuitive way to understand this?
So I'm not 100% sure. So I think, so as I said here, the uncertainty is coming mainly from the uncertainty in PT. Now, the
PT of the jet.
PT of the jet.
Yep.
Right. So in both in 0.2 and 0.4. So I think the PT of the jet in the leadlet case is probably larger in this particular plot compared to this one, that is the reason why this will be smaller.
Okay.
So basically, alpha is running, so mu will be larger,
itself.
and therefore that would be the reason it would be smaller.
I see. I see.
Go ahead.
Okay.
So you show it for the PT ranges between 40 to 60. Did you also calculate for lower PT regions?
Oh, lower PT. Oh, lower PT will be. I think the uncertainties will be super large because, I mean, once again, this is just scale variation. So the scale variation uncertainty will be very large. We didn't calculate it. The Alice bins are, I mean, the lowest Alice bins where they've analyzed the angularities are the 40 to 60. Is there a reason you asked?
Yeah, I was asking because you're inputting this splitting function, medium-induced splitting function.
Right.
There were some discussions that it is not perturbative, it may have non-perturbative components. And that may be visible at lower PT bins.
Yes.
Especially in the heavy ion case.
Right.
What do you think about it?
Okay. I mean, I would say well, the fact that it could, I mean, you're talking about Abhijit's work, basically calculating.
Yeah, and
Q
also
hadron.
before the Miklos and
Right.
Brook had,
Right.
so.
So, well, the thing that I can't quite see is how does going in small PT affect, like, directly correlate with the fact that Q hat is non-perturbative. I mean, the interplay seems to be quite complicated.
There may be more substructures in the medium which may provide kicks.
Yeah. Okay, so mainly the answer is at smaller PT, we have much worse control, so we didn't go to smaller PT. But yeah.
Question here?
Yeah, very nice results. I had a quick question about the ALICE data, right? I mean, it's has fairly large uncertainties.
Yes.
And I can't quite see, looking at the different colors, but are you able to compare to the A dependence? The modification, like I can't quite, see the ordering.
Oh, ordering, yeah, okay.
Possible to at least qualitatively compare if you.
Yeah, I think we got the same ordering.
It's the same ordering.
Yeah.
Okay.
Yeah.
Okay. Yeah.
But I think the crossing point is different, for example.
Okay.
But the ordering turns out to be the same.
Okay. It seems fairly R independent, right? The ordering and so on.
Yeah.
Oh no, so this is groomed in. Can you do is it possible to also do a groomed calculation for you guys?
We are thinking about it, but yeah, we can discuss more, but one has to put the grooming in the, just like a splitting function, put that in the observable and see.
Okay, cool. Thanks.
Okay. Any other questions? Well, if not, let's thank our speakers.